All right, welcome everyone to the ECE Department Colloquium. We are running this series this quarter. The topic is really issues surrounding solid-state circuits and integrated systems. And these talks are being run jointly with the IEEE Solid-State Circuit Society and the Circuits and Systems Society. And so for the students that are in the room, I would encourage you to join as a student member IEEE. It's really cheap. I forget the number, but I think it's like 20 or 30 bucks. And it really opens the door to a lot of activities, professional activities in the area. So I think it's a great thing. So we have a very special speaker today, and he's actually an alumni from this department. So he got his PhD at the University of Washington under Dave Allstott, who I understand is actually watching this live. Dave cannot communicate back in our direction. Maybe that's a good thing, I don't know. Oops, and now I lost your bio because this went to sleep. So I'm going to have to do this on the fly. He received his bachelor's in technology from the Indian Institute of Technology, Kharagpur, and then his PhD at the University of Washington. He was at Intel's Circuits Research Lab, CRL, from, I believe, 2008 to 2013. Mm-hmm. And then after 2013, he took a position as an assistant professor at the University of British Columbia, just north of us. So he actually drove down to give the talk. He really is interested in integrated circuits, optical systems, and wireless transceiver systems, all these types of integrated systems. He has a number of awards, which I cannot remember off the top of my head, but I do remember that he is currently a TPC member on the International Solid-State Circuits, for the International Solid-State Circuits Conference. He's also involved in the Custom Integrated Circuits Conference and Optical I/O. Was that the other conference you're involved in? Mm-hmm. So with that, it's my pleasure to introduce Sudip Shekhar, who will give today's talk on the future of what role silicon plays in electronics. So I'll let you take it away.
Thank you, Chris. Thank you for attending the talk. It's really great to come back to campus again and speak from this podium. I remember sitting where you are, maybe 20 years ago, 20 pounds less, and now it's great to come and talk to you. So I'll speak on how silicon circuits are now helping to integrate photons and electrons together on the same chip, and what all we can do with that. So here's my research group. These are the people that do most of the work. So on the top, I have students so my research group works on integrated circuits. I have several students working in silicon photonics. I have students working in clocking, and I have students working at RF and millimeter wave transceivers. And then a whole bunch of students who graduated, and then collaborators at UWECE and all across the world, and funding agencies are acknowledged there. So here's an outline of the talk. I'll start with the motivation, and then I'll just give a brief glimpse of silicon photonic devices. Can you hear me in the back? OK, thank you. And then I'll talk about silicon photonic circuits, and I'll give you a few case studies. And please feel free to pause, ask questions while I go. I would rather have you understand as I go along instead of just packing a few questions in the last 5 minutes. All right, so I'll start the presentation with a little bit of piece of history. Okay, so if you look at transistors, MOSFET, they were invented back in 1959 at Bell Labs by Atala and Kang. Okay, at around the same time, Mayman and Hall were working on lasers. Hall demonstrated the semiconductor laser in 1962 around the same time in the history. Okay? Things changed. Things took a very different turn after that. So I'm imagining most of you already know about CMOS technology and how it's changed our life. I'm not going to spend a lot of time on that. But if you look at what happened with CMOS technology, transistors were built, right? And then when people were building transistors, they figured out, well, if we add a resistor to this integrated circuit, we can make amplifiers. You can make amplifiers without adding a resistor as well, but that's a separate story. But adding a resistor, you make an amplifier. Then you add capacitors. You can do more interesting thing. And then people started to add more and more things on a chip. So people started to add inductors on the chip. Then there are a lot of things that you cannot add on the chip. And those things go on the printed circuit board. And then there was the electrical wire bonding. That was a way to attach things that you cannot build on the chip. So if you have a big capacitor, you put an electrical wire bond, and you connect the circuits to external elements. I believe last week, Danielle presented about crystal oscillators, right? You take a crystal oscillator, you wire bond it to your chip, your silicon chip. Okay? Our research is to not do that wire bonding, to bring it on the chip. But I'm talking about the conventional technology evolution here. And then attaching antennas. And now people are also putting antennas on chip at high frequencies. This is all known to you. The reason I'm pointing this because I'll talk about a similar thing that's happening with silicon photonics. OK, so if we look at silicon technology as a foundry, so foundry is you spend money and you give a design to a foundry and it sends a chip to you, right? So you are a circuit designer. You are not a device engineer. You are a circuit engineer. The focus of this talk is about circuits, not necessarily devices. So if we go back in time, around the early 1980s is when the first CMOS IC was available as a foundry. Okay? And then in 10 years or so, radio frequency CMOS circuits started to show up. A lot of people were skeptic, like, you're going to do RF on CMOS? Good luck with that inductor or transformer. And there are people in the room who built some of the first radio transceivers. And then around 2000, we had CMOS, a different flavor of CMOS. It was SOI. Okay? So this is so the SOI flavor of CMOS is, I'll talk about it in a minute. It came mostly for RF purposes. You can do better radio frequency circuits. And what could you all do? I mean, you can improve the performance of electronic circuits. You can improve the speed. You can reduce the latency. You can have more parallelism. Things are very, very compact in electronic circuits. You can miniaturize discrete electronics or bulky components, and you can make it on a small chip. And you can come up with entirely new applications. So this is all known to you, nothing new so far. Electronic circuits can have changed our lives. And if you notice, all of this is a playground for electrons. Okay? That's what we have. Electrons move, electrons are stored, and that's the motion of the electrons is controlled, and that's what we have on an electronic circuit. So around 2010-ish, and again talking about foundry, people figured, OK, well, why don't we repurpose the SOI CMOS process to do photonics on it as well? So the same silicon chip, why not do photonics? Okay? And once we have that, we can also now have photons on the chip and then have a playground where I have both electrons and photons that can work together to build new things as well. OK, so a question for you to think about. Why did it take, I started off that transistors and lasers came at the same time, right? In 20 years, we had CMOS circuits. OK? Revolution started to happen. Silicon photonics took another 30 or so years. Okay? Why did it happen? Why don't I not have a silicon photonic circuit in my iPhone? Like, why aren't there so many photonic circuits? Why did the revolution happen first in CMOS, first in electronics, but not in photonics? Are there a couple of quick answers here? Somebody want to talk about? Okay.
Do waveguides have tighter dimensions?
Sorry?
Do waveguides have more specific dimensions that they do?
Waveguides have more specific dimensions. Very good answer. So flow of photon is like flow of waves. And if you want to manipulate the waves on a chip, without having a lot of loss, without photons escaping as you bend your waveguides, then you have to have proper lithography and proper technology to have a low-loss photonic circuit. And that's why we had to wait. Like 350 nanometer transistors, not good enough. 250 nanometer transistors, getting there. 180 nanometer transistors, now we are talking. 130 nanometer transistors, okay, I can do good job with it. So we had to wait for lithography to get better and better, transistor technology to get better and better, so I can do better photonics on it. Okay, very good answer. Any other answer? Okay?
We're able to achieve a lot of high-level objectives with CMOS electronics, so there's no need to invest in photonics.
Can you repeat the first part?
Oh yeah, the CMOS circuits were really good, so there was no point in trying to make the photonic ones work.
Yeah, so the CMOS circuits are really good. There's no point in doing photonics. Hopefully, by the end of this talk, I'll be able to change your opinion a little bit.
Now it's changed.
Okay, all right, thank you. Any other? One more? I'm sure there are photonics expert in this room as well. Optics expert? Okay, so give it more thought. I'll come back to this if there's time, okay? There are a couple of big reasons why the electronic juggernaut happened much earlier, and it keeps going on. I mean, I'm not showing the FinFET technologies, right? But yeah, I'll come back to that. But now that we can do photonics and electronics together, there is a lot of things we can do. And as a student, you would also realize that if this is a new technology, there is a lot you can do. There is a lot of new things you can do. Right now, we are still doing baby steps in photonics and electronics together, if you look at it from the perspective of the last 50 years. So there's a lot of things to be done, and you do not have to be necessarily a device physicist to do that. This is a circuit problem now. This was not the case 5-7 years ago, but today it's a circuit problem, not a device problem. So just like electronics, I can use photonics to do very similar things that electronics did. So I can complement electronics to make things go faster with lower latency and lots of parallelism. I can miniaturize discrete or bulky optics. So for example, instead of having a LiDAR that goes on a Humvee that takes the entire top of the Humvee, I can make LiDAR that's this small on a chip. So I can enable completely new applications. So I can use optics to do biosensors on a chip. I can do quantum computing with optics as well. It's not an easier problem. It's actually a harder problem. So quantum computing is not an easy problem. But there are places where optics make a lot of sense and will enable new applications. Now, do not confuse silicon photonics with optical fiber. Okay? So one of the things I'm going to try to do in this talk is also break a little bit of myths about silicon photonics that you read in media. Oh, silicon photonics is going to change the world. Silicon photonics is low power. Silicon photonics is very, very, you can have lots of parallelism. I mean, as a circuit person, as a CMOS person, and a photonics person, I would like to make sure that there is a balance. So do not confuse the advantages of an optical fiber to that of a photonic chip. Okay? Optical fibers are awesome. They have very low loss. I mean, we're talking about loss in sub-decibels per kilometer, and they do not have frequency dependence loss. So if you have taken a wireless class, there's no what's called intersymbol interference for the kind of data rate that we have to handle. Then optical signal, do not suffer from electromagnetic interference and do not suffer from crosstalk. Again, I mean, I'm doing a hand-wavy claim, making a hand-wavy claim here. And you can have multiple data streams. So you can do what's called wavelength division multiplexing. So you can have multiple data on different quote-unquote color of the light, different wavelength of the light, all in a thin, narrow fiber. And this fiber is flexible. It's not bulky. So cable management is easy. So lots of advantages of optical fiber. And the goal, the driving force behind silicon photonics is data centers. So in data centers, we have racks and racks of servers that need to talk to each other. And if you use copper cable, they're very lossy. So we use optical fiber and what we call a transceiver. So these are the transceivers that look like bigger than these HDMI dongles here. And you plug it into the back of the server, and they carry data much, much faster than what copper can carry over long distances. So we use these optical fibers and these silicon photonic transceivers, that's in that little thing over there, to transmit data from servers to servers, between data centers, within a server as well. And there's a lot of work going on to actually bring optics closer and closer to the package, to even the efforts to put it within the package. OK, so a quick background. So let's say if I have a data is electronic. Most of the data is electronic, generated by CPU, stored in memory. So we have electronic data. But I want to transmit it over a larger distance. And let's say my channel is copper. So I have to send the data over a transmitter. And at the receive side, I'll receive it and make sure it's still digital. And if not, I'll amplify it and clean it up and make it digital. So if I use a copper channel, if I send my really clean 101010 pattern, so if I send my really clean 1010 pattern, the channel has a frequency response, could be very bad frequency response with a notch here. And then at the input of the receiver, my highs and the lows are not clean, and they all mix with each other as well. So these things are a nuisance at high speed for high-speed signaling. So let me walk you through how an electro-optical link works. So again, my data is still a bunch of digital highs and lows. And what I would like to have at the receiver, electrical receiver, is again high to low. But I'm going to use optics now. So first, I take a fiber, and I take a laser. Lasers don't like reflections going back into them, so we use something called an isolator. Think of it as a diode that does not allow light to propagate back into the laser and keep it stable. OK, this laser is a continuous wave, and the frequency is 200, let's say 200 terahertz. So that's one big difference. If you've taken an RF IC class from Chris and others, you know that RF radio frequency circuits use a carrier frequency. You use a carrier frequency in hundreds of megahertz to few gigahertz to 30 gigahertz, 80 gigahertz. We are talking about 200 terahertz here as a laser continuous wave. Okay? And just like the radio frequency circuits are designed, there's modulation that happens with this carrier frequency as well. So we take this laser's signal, this continuous wave light, and we put it on a photonic circuit, which is, let's say, what we call a modulator. And the modulator is connected with the laser isolator assembly with some connectors. And then on the receive side, we have something called a photodetector. So after the modulator, the signal is no longer, optical signal is no longer continuous wave. It goes high and low, low and high, and so forth. Based on the electrical data, I want to chop my optical signal to highs and lows. And then if I have that, what I need is electronics. Okay? So I would need, so optics is really good in carrying this signals, but I need electronics. And so the kind of things I need is I need amplifiers to take low speed, low amplitude signal, and I need to drive these modulators with high speed drivers. Optical circuits are very sensitive to temperature, so we need to have control electronics that also control the temperature or compensate for the temperature drift on the chip. On the receive side, I take my optical signal and put it on a photodetector, And that gives me electrical current, which is very small. So I need to amplify the electrical current into a voltage. And it's a transfer function of current to voltage. So we call it a trans-impedance amplifier. Instead of a voltage to voltage amplifier, it's current to voltage. So it's a trans-impedance amplifier. And then we amplify it and we feed it into my receiver. OK, so what has happened in the last 10 years is instead of putting these devices into as implementing a discrete modulator, discrete photodetector, we have built all of them in a silicon process and hence shrunk them down, made them really low cost, and that is into this transceiver now. OK, so that leads to silicon photonics. So what we see here is a process which is silicon on insulator. That's what's called SOI. And that is a process that people made for RF circuits and put a lot of effort into making it high volume manufacturing and hence low cost. So we just repurposed that to also guide or couple light into it, route the light, and then also have photodetectors to convert photons to electrons. So how does this look? Well, there are two flavors of it. Okay? One flavor is you have separate ICs. So you have the silicon photonic IC, which is a dedicated CMOS fab for photonics. Okay? And so this is your modulator detectors, and you design your drivers and your TIAs as separate chips, and you flip chip them on all of them on some kind of a package, and that's what is shown here. This is one of the work that we presented at ISSCC a few years ago. The other flavor is that you put all of them in the same chip. So you have electronics and photonics all in the same chip. It's called a monolithic approach. Okay? This is the best of both worlds. This is compromises in both worlds. Okay? But it has it has values in terms of reducing parasitics and the need for electrostatic devices and things like that. So there are pros and cons for each one of them. All right, myth number 1 that you often see, that photonics is going to replace electronics. Not going to happen. Okay? Why? Because if I look at a CMOS chip, in 1 square micrometer, I can have hundreds of transistors. Okay? Even the smallest optical modulator occupies about 100 square micrometers. So as an engineer, which most of you are, I believe, you have to make trade-offs and you have to make rational decisions. If something can be done really well with transistors, you're not going to do it with optics. Even though you loved photonics or you loved optics or you're a physicist at heart, you have to make choices, and you would make sure that you should make the right choices. So are we going to see photonics to move data within one chip? Like if I have an option to move data from point A to point B, smaller distances, are we going to use photonics to do that? Unlikely. We're going to use electrons to do that, not photons, because electronics switches are much smaller than photonic switches. OK, now let's quickly talk about silicon photonic devices. So on the silicon photonic chip, we have waveguides. We have splitters. So these are 3 dB splitters. If you've taken a microwave class or a millimeter wave RF class, you know what a 3 dB splitter is. Then we have 3 dB combiner, just a reciprocal of that. We have couplers and so forth. So these are what we call passive circuits that do not need any voltage to operate. And then we also have active circuits such as laser and photodetector, for which you need a bias voltage. OK, so coming back, silicon on insulator. Okay, so I have my silicon on an insulator. That's the SOI process. Why can I guide light? How can if I have a laser and apply it to a silicon photonic chip, how can I guide light? Because of total internal reflection. If you look at silicon, the refractive index of the silicon is quite high compared to silicon dioxide on the bottom and on the top. So if you send the light in, the light just gets totally internally reflected, and you can guide the light really well, and hence that means you can do now photonics on a chip. OK, myth number 2. Photonics is very low loss, or you can do things. Again, if I look at here, yes, optical fiber has very low loss, but photonic circuits still are quite lossy, about 2 dB per centimeter. Okay, physicists are working to make this loss even lower. So again, you have to make rational decision. If I have to move data, and if I can do it with electrons, better to do that. But again, speed matters. If I have to not send data at 20 gigahertz or 30 gigahertz from one point to another, maybe optics is better. So again, I have to make decisions. Thankfully, chips are not usually centimeter size. They're usually a few millimeters. So this loss is still very low. How do you attach things to a photonic circuit? This has been a problem for a lot of CMOS people, CMOS circuit people that have started to do silicon photonics. CMOS electronics is itself quite hard, as a lot of you would say here, right? Now, if I want to do photonics with it, it's certainly making my life even harder. Coupling the light to a photonic chip, you can couple the light at the edge, okay? You can couple the light anywhere on the chip using surface couplers. But what has come, a new technology that has come in recently in the last 2-3 years, has been commercialized, and we have the first machine in the world for it, is a photonic wire bonder. So if you have, let's say, a fiber, and you have some photonic chip, and this is, let's say, quote-unquote pads on the photonic chip, you just use the photonic wire bonder to connect the circuit. And this, we believe, is going to make the life of photonics, life of CMOS people, circuits people, to jump into photonics much, much easier. If I can now use just a photonic wire bonder to connect my circuits, you can just stick to circuit design and make the packaging much, much easier and testing much, much easier. And knowing so many of you being students, you'll be in the lab doing a lot of testing. Anything that helps with testing is awesome as far as the student is concerned. OK, so I'm going to talk about a few circuits, ring resonators and interferometers. Okay, so what's a ring resonator? Let me walk you through it. It's very, very simple. I have a light coming in, okay, and I implement what's called a directional coupler. So the goal of this directional coupler is to introduce a phase shift, okay, a 90-degree phase shift if the light leaks in here. Then the light goes around, okay, and then gets another 90-degree phase shift as it goes out of the coupler, okay? So the total phase shift as it goes in and goes out is 180 degree, okay? If the light, as the light propagates on a waveguide, it accrues phases, okay? So what happens if the ring is designed in such a way that the phase shift as it goes around the ring is 360 degree or multiples of 360 degree? What's going to happen? Original light keeps on going. Any light that goes back and joins it here sees a phase difference of 90 plus 90, 180. There's a destructive interference that happens at the output. So only for a specific wavelength, when the phase shift is 360 degree, you don't get anything at the output. No, nothing comes out at the output. And then, because 360 degree happens at multiple integers, you have multiple wavelengths at which you don't see anything. You've made some of the world's best notch filters. Okay? And if you have made a very good notch filter, now you can design sensors with it, you can design modulators with it, and so forth. So we'll talk about one application for this. And another application is interferometers. You probably learned about this in some basics in engineering class. If I have a light coming in, if I split the light half and half in intensity, or 1 by square root of 2 in electrical field, and if I apply a phase shift in one of the arm, then the output phase shift is e to the power I phi of the input field. Add them up together. Okay? So you get an expression of output electrical field as the sum of two things. Again, and if you do the math, output intensity has this transfer function. It's input intensity by 2, 1 plus cos phi. Okay? Now, I'll tell you how to do phase shift in a minute. But if I now want to do intensity modulation of the light, I can use a phase shifter to do intensity shifting. Okay? In silicon photonics, it's not very easy to do intensity modulation at high speed. So we use phase shifting and this indirect way to do intensity shifting. So if I somehow figure out a way to do phase shifting, then by changing the phase, I can have output intensity completely equal to input intensity, or I can have 0 at the output. So I can do constructive and destructive interference. These are the only 2 circuits I'm going to talk about today, and we'll play with them, okay, in a couple of minutes. Now, last slide is how do I do the phase shift? There are 2 ways to do phase shift. One is a lossless way. Light goes in, you don't have any loss, light goes out, okay, and you do phase shift. The way to do that is to heat the waveguide. So you put a metal resistor next to the waveguide, you send a current, you have Ohm's law helping you, heat is localized here, it changes the temperature, local temperature of the waveguide. The change in the temperature changes the refractive index, and that changes the phase shift here, okay? So obviously, the circuit people here will be like, wait a second, that looks like a very inefficient way to do phase shift. You're actually burning power to do phase shift? Yeah. So it's consumes a lot of power. It is slow because to move heat in a chip at high speed is not easy. But it's lossless, so you don't lose photons going from input to output. Another is similar to transistor. Or diodes, why don't we dope the waveguide with P or N carriers? And then I apply a battery, okay, I apply a signal. Then what I would get is at the output, I'm going to get a phase shift, which is a function of the input voltage. And I can make my input voltage 10 gigahertz, 20 gigahertz, 30 gigahertz. I'm going to see output phase shift at that 10, 20, 30, 40 gigahertz. So this is very, very high-speed circuit. Typically, 50 gigahertz modulation is what you can get out of this. But there is loss in the output, so there is some loss. But in terms of power consumption, the power consumption is very low as far as the actual modulator is concerned, because these are usually reverse bias diodes. Okay? Next myth. A lot of times you would read Photonics paper, and they will say it's very, very low power. Okay? Well, yeah, it's very low power because if you look at the modulator, it's reverse bias, it's not drawing any current, right? But to drive this voltage, this modulator with high voltage, I need to design electronics with large voltage swing, and that electronics consume power. Okay? So together, if you're building a product, you're going to be burning a lot of power. Okay? But if you're just talking about photonics, it looks really good. It is good. It's awesome. But you have to look at the bigger picture.
Quick question?
Yes?
Actually, a couple questions. So what kind of voltages are we talking about for something
So what
like
kind
this?
of voltages are we talking about? Awesome, Chris. That's my next slide.
Okay, so let's save that one for the next slide. What's the linearity for something like this? I don't know if that's a later slide.
Yeah, so what's the linearity of this? So if we look at the linearity, it's quite linear. So phase is very linear. So if I apply a plot of voltage versus phase plot, okay, then it's very linear. Okay? But I just told you in a previous slide that phase modulation is linear, but if I want to do intensity modulation, I have to do this interferometric device, and that makes it nonlinear. Okay? And I'll also talk about that in the next slide. Okay? Okay, so now I know that I can have doped diodes, and I can make modulator out of it, but I want to do intensity modulation. That means I would put a phase shifter here. Okay? So let's do that quick. I had output intensity as a function of the cosine of the phase shift, and that phase shift is proportional to the voltage. So to answer your first question, Chris, phase shift is directly proportional, linearly proportional to the input voltage. Awesome. But intensity is not. It has this cosine nonlinearity. So if I look at phase shift or input voltage on the x-axis, then the output is nonlinear, highly nonlinear. Okay? And that tells you that if you have to not design the driver, and if you're doing amplitude modulation, the driver has to be very, very linear. The driver has to linear, but not only that, it also has to compensate for this nonlinearity. So one way we can do that is to bias this circuit at a point where it is linear. So don't bias it here, don't bias it here, bias it as right at this point. It's called the quadrature point. And at that point, if you apply a voltage, large voltage, then you get 0 at the output. Okay? So again, this is my voltage axis. This is my intensity axis. So if I apply a large voltage, I get almost 0 output intensity. If I apply a small voltage, I get almost all the output intensity. So we call this optical 1, and we call this optical 0. So if I have high-speed data, 1, 0, 0, 0, 1, 0, 1, 1, 0, corresponding to large voltages, I would get zeros here, and corresponding to low voltages, I'll get a high here. So Chris had a question, how large this voltage has to be? Okay? This voltage is called V pi, because this is the amount of voltage I need to introduce a pi amount of phase shift. Now, V pi typically for 30, 40, 50 gigahertz modulators is a couple of volts, 3 volts maybe. Okay? And it's a trade-off. So if you make your modulator very, very long, then you would need small voltages. If you make your modulator small, you would need large voltages. Well, if I go and buy a discrete modulator, it will be this big in length. I would probably need smaller voltages. But on chip, I make my modulators very small, couple of millimeters long. So if I make them small, I have to apply large voltages. This is the problem. It almost would remind you of a power amplifier in an RF circuit. You need to have large voltages from the driver, and it needs to be linear, but also compensate for this nonlinearity if you have larger excursion. Does that answer your question, Chris?
Yep.
Okay. All right. So, yes?
So the waveguide itself, are you restricted to sort of minimum diffusion widths, or do you get to play with those rules to make them really narrow and boost the count?
It's circuits. It's parameterized. Look at so you can change the length, and changes the modulator shape. So that's a trade-off you can make. Yes.
So will this be different for every wavelength that comes through that?
It is. So it is a function of the V pi L product is a function of the wavelength as well. But remember, optics has so much bandwidth, right? Like a nanometer or 2 nanometer of wavelength in optical bandwidth is, lots of electronic bandwidth. So usually not that of a concern. Okay, so usually what we do is, V pi L is, let's say in a given process, is 2 volts centimeter. Well, if that means that if I have to make my length larger so that I can make better, if I make my length large, I can have easier life in designing CMOS drivers. But large L will increase the loss of the waveguide, and my laser will lose power as it goes around this arm or this arm. Now, if I need large V pi, that means power consumption of the driver would be high. I would have reliability issues, breakdown issues. So what we do is, we'll just live with performance. So instead of going from almost high to almost 0, we only go to a finite high to a finite low, and the ratio is what we call the extinction ratio. Okay, we're like, in this swing, I don't need full rail-to-rail swing. I can live with lower amount of swing, and the receiver person will fix it. We'll figure out a way to amplify it. So we typically stick with millimeter long modulators and only apply a volt or 2 on it, if we can. But a few volts is not uncommon. 3 to 5 volt is also not uncommon. Okay. So so how do you design this circuit? So this driver needs to drive this modulator. This modulator is a millimeter long or 2 millimeter long, and it's carrying 10, 20, 30, 40 gigahertz of signal. So you wouldn't design it as a transmission line. Okay? So these electrodes, these metal electrodes, are not just designed as a wire. You design it as a transmission line. what's nice about a transmission line compared to a wire? So nice thing about a transmission line is if you just draw a random wire, it will have resistance and capacitances, okay? And it will be very lossy at high speed, okay? And I'm again giving you a very hand-wavy. If you design it as a transmission line, you can control the inductance of the wire as well, okay? And if you can control the inductance of the wire, then the inductance and capacitances will cancel each other out or try to cancel each other out, and that will extend the bandwidth of your line. Okay? So anytime you have to go longer distances on a chip, on a board, you should think about designing it as a transmission line for a given frequency that you're trying to transmit on it. Okay? So we design it as a transmission line. So that's one thing. So we need to make sure that there is a characteristic impedance, typically 50 ohm. So then you need to design the driver with a 50 ohm output termination. And you need to also terminate this transmission line with 50 ohm as well so that there's no reflection and so forth. And then another thing you have to do is you have to match the velocity of the optical wave to the velocity of the RF wave as they propagate together on the transmission line. Okay? So you also have to make sure, and often this velocity matching between the RF wave, the radio frequency wave, and the optical carrier wave is often a limitation as how fast you can make the modulator. Okay, now let's do some case studies. So first I'm going to look at a Mach-Zehnder modulator and a driver. So how do you design a driver? Very basic example. If I have, and I'm going to design a differential driver. You know the advantages of differential circuit, and so we'll stick with that. So if I have a driver, and as I have a Mach-Zehnder modulator with two p-n junctions, then I'm going to design a driver such as shown here, which is a differential amplifier with a current source. With source resistances here RT, which is 50 ohm, 50 ohm, if these two transmission lines are 50 ohm. And I also terminate these at the other end of the electrode to 50 ohm as well. If I look at current that flows in, so let's imagine that this transistor is turned on, and this transistor is turned off because I'm sending a 1 and a 0 here. All of the current is going to come from two places. It's going to flow like this, or it's going to flow like this. But no current will be flowing here. And what you get at this voltage here, VP, is VDD minus IR. And the voltage here, there's no IR, so this is VDD. If you switch your inputs, the output voltages switch as well. So if you look at the differential swing at the driver output, it goes from plus RT IT by 2 to minus RT by IT by 2. And that should be enough to give you an optical high and an optical low. So the way to have higher swing is crank up the current. But if you crank up the current, your transistor may go into a triode region. If you crank up the VDD, you'll have reliability and breakdown concerns. So a driver design looks very simple, but it is quite challenging. And you can, again, use circuit techniques such as having an inductor in the driver as well, adding a cascode to improve the reliability, adding an inductor to absorb some of the capacitances of the circuit and speed up the circuit. So, yes?
Does the inductor change the voltage division at the transmit side?
So the goal of this inductor is that it absorbs the capacitance. It's a low Q inductor. So the DC is not, there's no DC drop. Okay? And as far as the AC is concerned, so again, the goal is to mitigate the capacitances. So adding an inductor is almost coming mostly at the expense of area, but doesn't really reduce my swing. In fact, because it absorbs the capacitor, the capacitance, it improves the edge rate, and it improves the swing.
I guess my question is, looking into the source, you no longer have RT across all frequencies, which you expect for perfect matching on a transmission line. You now have RT plus LS in parallel with whatever cap. Does that play nicely with division?
Yes, yeah. So the reason we added an inductor is because there was a capacitor sitting here. So the goal of the inductor is get rid of the capacitor and show me RT at higher frequency as well.
But at one frequency.
So at one frequency, ideally. So, but by making this inductor and capacitor and resistor play with each other, it is not a very sharp resonance circuit. It's a very smooth resonance circuit. So you see RT for a very, very broad frequency range. OK, so this is how a transceiver looks like inside an Intel transceiver, for example. So you have your Mach-Zehnder modulator, OK? And you have drivers. And you also need to have control circuits, because these Mach-Zehnder modulators will also have process variation. So then you design these low-speed control circuits with ADCs and digital controllers to make sure that you're really biased at the right point. Just like the way you bias a transistor, here you bias the optical circuit at the right point. And the biasing is done, again, by using heaters. If you want to do more complicated transmission, so on-off keying is only going to get you so much. If you want to do 2 bits, so let's say on-off keying, I only have 1 and 0 as my alphabet. If I have 0, 0, 0, 1, 1, 0, and 1, 1 as an alphabet, then I can transmit 2 bits in a given amount of spectrum instead of a 1 bit, because I have, in a given amount of time, I'm sending 2 bits. But now I have multiple amplitudes. And that means that my driver has to be linear as well, because now it is doing PAM4, pulse amplitude modulation, 4 levels of PAM4. And it has to handle the raised cosine nonlinearity of the modulator as well, coming back to the question, Chris, that you asked. That the moment I go from any kind of multi-level amplitude modulation or phase modulation, now the nonlinearity of this circuit is a problem, and I need to compensate for that. OK.
Can you give a sort of a ballpark metric for that in dBm, like IP3, or I don't know how you would, what nonlinearity you actually measure this with, just for an idea?
Yeah, so we usually use total harmonic distortion as a metric, because these are broadband circuits. So if we talk about IP3 or P1 dB, we'll have to specify it at several frequencies. Where if we go in the THD domain, we just combine all the harmonic distortion terms and come up with a number.
Like a THD?
THD, yeah. Oh, like a THD? Oh, we're talking about 1%.
Just a quick question, since we're here. Why can't I simply pre-emphasize the...
We do that. Yeah, okay. So to compensate for this nonlinear cosine, we do equalization. OK, we can also do, just like in radio world, long time ago, we had amplitude modulation. And then we moved to amplitude and phase modulation. So QPSK and 16 QAM, which has amplitude and phase modulation, so both I and Q phase. We are now moving toward these quadrature amplitude modulation for silicon photonics as well. Why? Because we want more and more data rate. So by the way, the data rate that we're talking about in silicon photonics is in hundreds of gigabits per second. So this is not 20 megahertz or 100 megahertz LTE bandwidth. We are talking about hundreds of gigahertz bandwidth. Okay? So one of the things that we have shown recently is that just by using phase modulators, you can do a lot. You can come up with circuits that does amplitude and phase modulation. So you can have multiple drivers ICs, multiple driver ICs, multiple modulators, and you can come up with circuits. So these are circuits, not devices, that can do QAM16 modulation. And then because now you have, this is optics we're talking about, we can also do polarization, so X polarization and Y polarization. So we can take the circuit, copy paste it again, and use something called a polarization rotator, polarization splitter and rotator, and get 250 gigabits in here and 250 gigabits in here. So half a terabit per second we demonstrated a couple of years ago at ISSCC with the silicon photonic chip. Okay, so you can now, in the last 2-3 minutes, I'm going to give you a glimpse of what's happening. Okay, so the silicon photonics industry is driven by transceiver, high-speed transceivers. Okay, so I talked about how we can complement electronics and extend it and make it faster. Now I'm going to talk about how we can now come up with other circuits that have never been done before or tried and failed multiple times. So for example, if you look at accelerators in data centers, okay, one of the things that they do repeatedly is multiply and accumulate, multiply and accumulate. Okay? Now if you look at your a digital CMOS chip, so this is a so you take two numbers and you multiply them together and you accumulate them. That's your MAC, right? Multiply and accumulate. If you look at a digital CMOS and latest greatest digital CMOS, typical clock rates that you're going to run it, let's say you have a 2 gigahertz operation, it will have 100 nanoseconds of latency and consume about 1 milliwatt of power. Okay? Well, we can do multiply and accumulation at tens of gigahertz. Okay? Fantastic. Tens of gigahertz using optics. So if I figure out a way to have my input numbers in the electrical field of the light, then I know that this phase shift in the interferometer is nothing but a multiplication to the electrical field. And I can also use these splitters and combiners as adders. Okay? So using analog photonics, I can do MAC operations at very, very high speed. So if I compare the latency of an analog silicon photonic MAC to a digital CMOS MAC, we are talking about 1000x latency reduction. And in accelerators, latency is crucial. I mean, you are doing your web search, and if your Google has to complete your search result or even predict what you're typing, I mean, latency matters. Bandwidth is orders of magnitude smaller, but the power consumption, you have to be careful. If you just look at it from the photonic point of view, the power consumption is small, but when you talk about the system, power consumption is quite high. Okay? Often something that is not talked about. Power consumption of the whole system is quite large, but if your goal is to reduce latency, it's worth it. Okay? Precision is also about 8 bits. So inference is good, training, challenging. So here's a latest accelerator card from a company called Lightelligence, and this is your photonics chip, okay, and 8-bit photonics MAC. But what you see here, and this is your fiber going out, but again, for every photons here, you see how much electronics. I don't know if you can see it from the back, but there are lots of chips here, lots of electronic chips. So lots of controls, lots of high-speed drivers and detectors, receiver circuits. And then finally, the last couple of slides, I'm going to talk about something that cannot be done with electronics with the kind of precision that we are talking about. Okay? And that is with, if you're trying to detect a biosensor, if you're trying to detect COVID alpha and beta and delta and Omicron in a low-cost biosensor with quantitative metrics, not just hide that you have COVID or not, but what is the concentration of the COVID molecule. This is one technology that optics is awesome for doing. So let's say I have a biosensor, okay? Some kind of surface, and I've coated this surface with receptors. So these receptors are specific coatings that when I send a light through it, doesn't do anything to the wavelength of the light. It remains the same. But if I have some analyte, let's say it's a COVID molecule, okay, that analyte when I flow analyte through this, whether it's blood, whether it's, let's say it's blood, then those analytes will bind to my receptors, okay? And the presence of the analyte means my wavelength of the light changes. Okay? So that's how an optical biosensor works. Now, can we use silicon photonics to build this circuit? Because if it's silicon photonics, I can potentially make billions of these chips. They would be really, really low cost. And then I can have this part of the circuit functionalized for alpha, this part of the circuit functionalized for beta and delta and so forth, all in a small form factor. So yes, we can do that. We can make really good notch filters of quality factor 50,000, right? 40,000, tens of thousands. So if I have this ring resonator and send my light in and send my light out, if you recall, earlier I talked about that the transmission as a function of wavelength has this notch response. Okay? So this is just one ring on a chip of a diameter of, let's say, 20 microns. Okay? Now, let's say I coated it with a specific receptor, and I sent my analytes of interest, COVID molecules. It will bind to this surface, and because the light is propagating in this waveguide and in this waveguide, and a very small portion of the light leaks out, and that leakage is going to interact with this analytes, and that is going to change the refractive index of my waveguide and change the resonant notch wavelength. This circuit is so sensitive because it has a quality factor of tens of thousands that even this small amount of interaction here can make a very sensitive sensor, and that has been commercialized recently. So there's a company in San Diego called Genelite, and they have these ring resonator-based sensors, and they guide the light in, and they send analytes on it. This is how their cartridge looks like. And they have emergency approval for COVID detection and other things. What we are working on is to take their $50,000 design, which is mostly photonics. So they have a tunable laser, cost $10,000. They have these nanopositioners and robotic assembly to guide light, cost tens of thousands of dollars. And then they have silicon photonic chips that cost pennies. Okay? And then they have detectors, which again are very expensive. The whole thing is very bulky for lab. What we are working on is put your electronics hat on. Okay? Why do I need to have $20,000 worth of laser if I can buy $1 cheap laser? Okay? Why have complication in photonics and mechanical engineering, like in robotics and detectors, if I can put complication in my circuits? So I know I can do phase shifting. I know I can do electronic and photonic design. So I can make the entire this printer-sized machine into a chip because I know my electronics and photonics. And that's what we are working on. So this is the Genelite machine. And we haven't published this yet. We have just published something in an invited paper, hopefully coming later this year. We can't talk about it much right now, but yeah, all the electronics and photonics, it has ADCs and DACs and phase shifters. All of this can be done in one chip, working with COVID. Okay, so to conclude, if you're an electronic designer, if you're a photonic designer, photonics is awesome in certain things. Very high speed, very low latency. If you're designing sensors, very, very sensitive. Very wavelength sensitivity is quite high. So lots of great things. Electronics has lots of great things. The electronics is small. It's easy to design for transistors. So use both of them together to come up with silicon photonic applications. And I just gave you a couple of examples. But a lot of people here are working on LiDARs and phase arrays and gas sensing and quantum computing and so forth. So that's it. Thank you.
Okay, that was a really good talk. All right, so let's open it up to questions. Yes.
Yeah, thank you, Professor. for
Very
that.
loud.
Yeah, thank you for the talk. We talked a lot about photonic devices and how they can be used, but I want to get a bit more sense of the contributions your lab has been making. So, is one question to start is so with the whatever, I don't remember what the San Diego company was called, but so are they not integrating everything on ICs, or I'm just wondering what, from an architectural perspective, what does their system look like compared to yours?
Yeah, so what they have, the company Generalite has, is they have a laser that sweeps wavelength. It's called a tunable laser, okay? They come in boxes that are this big, okay? And they have, because these lasers are expensive, you cannot have many of them, right? So you have only one laser, but you have many, many rings, right? So now you have to have this robotic thing that takes the laser output, moves it here, moves it here, moves it here, so that it can excite each of the rings, right?
Mechanical switching?
Yeah, so it's very complicated, right?
Yeah.
But I can have a single fixed wavelength laser, cost $1 in high quantity, and I can use a whole bunch of splitter on a photonic chip, more complicated photonics. I can have tunability on a photonic chip if I have electronics with it as well, right? We know how to make tunable circuit as an electronics engineer, right? So electronics and photonics, I can certainly do a lot of tunable circuits. So I can mimic this wavelength sweeping of the laser by sweeping the notch frequency of the ring resonator.
Okay, yeah.
Does that make sense?
Yeah, so their photonic platform doesn't have any electronic input or tunability.
Hmm?
So do you use, like, is some monolithic integrated chip or that you use, or?
So we have both versions. So one is in Global Foundry monolithic platform, and the other one is a TSMC chip co-integrated with a silicon photonic chip.
Good. Just a quick reminder: if you're signed up for credit for this this Colloquium series, make sure you sign the attendance sheet before you leave. It's in the back with Isaiah. Okay, more questions? Yes, Cole. Loud.
I see you can use these really small lasers that you can actually integrate on the chip. Is that right?
Yeah, so a lot of people, device people are working on integrating lasers on a chip. It's not an easy problem because silicon does not lace very well at the wavelengths we want. Our approach is photonic wire bonding. We just buy a chip, just like a crystal oscillator. We buy an off-the-shelf laser, and we use photonic wire bond to slap it on next to my photonic chip.
What's the power requirement on something like that?
The power requirement is dependent upon how much loss you have, but the laser that we are looking at is 10 milliwatt output power. So,
Good. More questions? Yes.
So in regards to the biosensor you're talking about, I'm curious, like, how does the process of like interpreting that data work? Like, pretty much once you get these different readings, like, how do you know that this correlates to like this many cells and what types and all that?
very good question. So, what I'm measuring is a proxy. So I'm measuring the change in the wavelength, right? And I need to relate it to the presence of the analyte, and I also need to relate it to the concentration of the analyte. Well, awesome thing is that this thing happens slowly. It also gives me the kinetics of the reaction, how the analytes are binding. I can also get kinetics, which is a totally different machine called SPR, surface plasmon resonance, costs $200,000. I can do all of that. And now, because my rings are very, very small for photonic sense, we're talking about tens of microns of diameter, I can have many of this. And then I can have, I have robustness because I have many of them, but I can also now do very clever algorithmic post-processing of the data to get rid of the noise, get rid of do common mode noise, get rid of other unwanted bindings that we see in certain parts of the sensor. So once you have lots and lots of sensors, you can do much more data processing on the back end.
Thank you. That was a great answer. Thank you.
And this, my vision, my belief is this is the future of biosensing for medical diagnostics. You absolutely need to have lots of sensors on a chip, and that gives you so much data that, data and machine learning for biosensing is an untapped market, and there's a lot to do there as well. But we need cheap sensors. Machine learning became big because we have big data. And why do we have big data? We have cheap servers, right? And cheap GPUs. So we need lots and lots, billions of biosensors, so to generate the data that we can do machine learning. And so for that, we need to go to chips.
Good. OK, I think we'll probably wrap it up there because we're going a little over time. Let's thank our speaker one more time.